Welcome to Jupiter.
This NASA team has just put a spacecraft into the closest orbit ever around Jupiter. Juno is now face-to-face with the harshest planet in the solar system. I'm Dan Riskin. I'm on location here at Jet Propulsion Laboratory in California, where the energy is sky high. In mission control, they have just performed an incredibly dangerous maneuver, bringing their spacecraft inside Jupiter's deadly radiation environment to put it into orbit. Here's more from that historic moment when Juno called home to say it had survived.
You could have cut the atmosphere with a knife. It was so tense.
Systems, this is Nav.
Go ahead, Nav.
We see the expected sharp shift upward, indicating the main engine has started.
Almost there.
It's taken 10 years to get to this point.
Welcome to Jupiter.
NASA did it again. And I am so happy to be part of the team that did that.
After a 1.7 billion mile journey, we hit our burn targets within 1 second. Isn't that incredible?
Over the next hour, we'll show you how they engineered Juno to be part spacecraft, part science laboratory, and part tank to survive Jupiter's fury, and why it's worth it. Because it could unlock the mysteries of the origins of life, second off from exactly what it was supposed to be. And this is just the beginning. Now, Juno is going to skim the cloud tops of Jupiter right up against that deadly radiation. But scientists say that studying this planet is worth the risk.
Jupiter is a planet on steroids.
It's the bully of the solar system.
More than 1,000 Earths could fit inside.
You could take every planet and every comet and every asteroid in our whole solar system, and they'd fit inside Jupiter.
It's Jupiter. It's the cake.
In 1973, Pioneer 10 made the first encounter. Pioneer 11 and Voyager followed, skimming Jupiter's clouds from a safe distance, giving clues to a massive magnetic field and deadly radiation. In 1995, Galileo became the first to orbit and to launch a probe into Jupiter's atmosphere. Now, Juno will go 9 times closer than any before to unlock its secrets and those of the solar system.
It was probably the first planet. It used most of the leftovers after the sun formed.
Its gravity affected how all the other planets formed.
If you want to figure out the recipe of a solar system, which is really what I want to do, then figuring out how Jupiter formed is that very first step in that recipe.
Scott Bolton is the lead on the most daring mission to Jupiter yet.
I've been wondering about Jupiter most of my life.
But piloting near Jupiter's violent and destructive atmosphere is not only risky, it's unprecedented.
We're going to go into the throat of hell.
It's very stormy.
It's just this huge ball of gas with swirling winds and ammonia clouds, water clouds. You start going down, you've got storms, lightning.
Super bolts of lightning, thousands of times more powerful than the lightning bolts on the Earth.
For these reasons, Juno must proceed with caution.
Let's imagine that you could travel down through Jupiter.
We wouldn't land on the surface. We would go through the clouds, going down, down, down.
Keep going deeper and deeper.
We'd feel all this pressure of the gases on top of us.
And soon it's not like a gas. It's kind of like a fluid.
A liquid metal like mercury.
In the middle of it, it may even be solid.
We think deep inside the planet, there should be a dense core, probably 3 and 20 times the mass of the Earth.
We really don't know.
They don't know because this is the first mission that dares to get close enough to truly measure the gravity of this giant. To do that, Juno needs to handle Jupiter's super spin, 1 full turn every 10 hours. All of the rotation stirs up the metallic hydrogen thought to be inside. The result? A massive magnetic field that traps all kinds of deadly radiation particles.
So toxic that humans wouldn't even survive a second there.
What we're going to learn with Juno is what is the dynamics that drives that magnetic field. It spreads out to up to 100 times the size of the planet. There's a tail that extends all the way out to the orbit of Saturn.
It's the first time we're going to see how bad it really is.
To survive a radiation belt 1,000,000 times more intense than Earth's, they've armored every part of Juno, even the massive solar arrays. As the first mission to risk flying up and over Jupiter's poles, it will capture the best light show in the solar system.
We see this beautiful ring of aurora on Jupiter. I want to know why it got there, how this process works, and how does it all fit together.
Juno will even attempt to pull back the veil on the famous Great Red Spot.
The Great Red Spot looks a little bit like a hurricane on the Earth with an eye and it's swirling around. It seems to suck up other storms that get near it.
Who wouldn't like to fly into the Great Red Spot, swirling around orange clouds?
There is so much riding on this mission. If Juno succeeds, a 5 billion-year-old treasure chest will be opened.
What are we going to find?
The secret to how the solar system formed is inside Jupiter.
We want to know where we came from, Earth, life. And Jupiter kind of holds those secrets.
To get at those secrets, the team had to build the most rugged spacecraft ever, one that could survive 20 months in the harshest environment in the solar system, one that could survive radiation equivalent to 100 million dental X-rays over the course of the mission. They had to build the toughest ship in the solar system.
To survive this,
It's pretty bad.
they had to build this.
We use titanium, a little bit like Superman uses lead to shield him from kryptonite.
This is Juno, a mighty spaceship up against the biggest bully in the solar system. It's the mass of a monster truck, a spinning hexagon with 3 enormous solar arrays, each one the length of a bus, designed to get Juno to Jupiter.
Sending a spacecraft to Jupiter is not that easy. We better think outside the box.
The greatest challenge of getting close to Jupiter is surviving its intense radiation.
Nothing compares.
It won't be easy.
What did I get myself into?
Bill McAlpine and Heidi Becker are among the most scared. They're the radiation gurus of this mission.
Imagine having bullets moving close to the speed of light, bombarding your spacecraft, punching holes through it, creating noise in your detectors.
The more radiation you get, the worse the parts behave. And at some point, the parts just simply won't work properly.
Juno is going where no spacecraft has ever gone before. It's a frightening enough place that you're going to that you don't want to leave any stone unturned. You just test everything.
The team had to take their best shot at replicating Jupiter's intense radiation at an underground nuclear lab in Troy, New York.
We are pretty much known in the community for radiation testing. This is one of the few facilities that can offer that.
Yaron Danon is an expert at creating hostile environments. This linear accelerator mimics the radiation Juno will encounter at Jupiter.
We provide a field of radiation which is similar to what they see in space. It is an environment of electrons that are around Jupiter.
Here, they direct an electron beam at Juno's key parts. First, and most important, Juno's star tracker.
The star tracker is the eyes of Juno. It tells Juno where it is. It tells us where our data were collected. And if the star tracker doesn't work, we don't understand our data.
They hammered the sensor over and over with high-energy radiation to see its breaking point.
The most important thing that we learned was that electron bullets make different-sized bullet holes depending on their energy. And that told us we need to test with the energies that we think will get into our shielding.
Now, at Lockheed Martin in Colorado, they could begin to build the shields they would need to protect a spacecraft going to Jupiter. They turn to the stuff that the military uses to build fighter jets and tanks. Titanium.
Juno is an armored tank. It's got a huge radiation fault in the center of it with thick walls of titanium all around it and all these sensitive electronics inside.
Without this titanium shield, Juno's electronics wouldn't even survive the first flyby. The constant bombardment of particles would charge up the key circuits, wiring would fry. Outside that vault, everything is exposed.
We also had to protect the solar cells from the radiation, so they have a cover glass over them.
Glass is the perfect shield for the solar cells because it allows the light through. But at the same time, the radiation at Jupiter is charged, so it'll slow down as it goes through the glass.
Built to survive, Juno must also endure rigorous testing. To see if Juno can handle frigid temperatures 5 times what we'd see at the Arctic, the spacecraft goes into a massive torture chamber.
We heat it up, we cool it down, and in fact, we go beyond the temperatures that we expect to see in space to make sure that the spacecraft will perform.
The final weeks to delivery are unforgiving. A relentless schedule, no room for error.
It was a very intense time. Several hundred people were all busily working through this whole process.
We worked a lot of weekends, we worked a lot of second shifts.
When it finally got on the pad, just seeing it there and knowing that we were done was a real sense of relief.
But that relief is diminished as Juno faces its ultimate test.
We're very confident we've done everything we can.
But I'm a little worried that when we get there, that we're going to find out that we weren't completely right.
We did it. We conquered Jupiter. Scott Bolton, principal investigator for the Juno mission. Did you get it completely right?
Truth is, I don't know yet. The spacecraft performed flawlessly. We got that part right. But we don't really know what environment it flew through. We're going to have to wait till we go by with all our eyes and ears on. And then we'll know if our models are completely right.
So leading up to Jupiter orbit insertion, you did a lot of worrying about a lot of things. You're a worrier. What are you worried about now?
Now I'm worried about what did Juno just go through? And can it survive when all the instruments are on? Because that's still a little bit of a question. So, you know, when you go through a critical maneuver, you tell the smart robot, fire the rocket no matter what. I don't care what problem you think you see, ignore it and fire the rocket. Now we go into normal mode where if the spacecraft sees a problem, it calls home. So we've still got to see how we're going to perform scientifically.
Well, thanks so much. Coming up.
And liftoff.
The team faces its first big challenge.
It's getting very real.
A 5-year trip to Jupiter.
Five, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter.
It all began August 5th, 2011, when Juno blasted off from Cape Canaveral, Florida, tucked inside the nose of a gargantuan Atlas V rocket.
Everybody was tense, everybody was confident, but at the same time, you're kind of holding your breath a little.
Engine response looks good.
To get enough thrust for liftoff, the Atlas V burns through over 500 tons of explosive fuel.
That moment of launch is when you put the spacecraft at the most risk.
And we have solids 1, 2, 3, 4, and 5 jettison.
After the solid rocket boosters are spent, the main engine of the Atlas continues the climb.
Current altitude is 45.8 miles. Velocity 5,413 miles per hour.
4 minutes and 45 seconds after liftoff, the nose cone opens to reveal Juno, and the first stage of the rocket falls away.
And stage separation.
A final push from the upper stage of the rocket sets Juno free. Then, a crucial step has the team holding its breath.
The solar panels have to open up after the spacecraft's launched, and you can't test that on the ground. We don't have zero gravity here on the ground.
The enormous solar panels had to be folded for launch. If they don't unfurl perfectly, Juno will have no power for the long trip. The deployment is flawless.
I don't know if you can see it on my face now, but it was exhilaration and a sense of relief at the same time.
There's still one final step to get Juno on its way. The spacecraft needs to make a 2-year loop around the Earth for a maneuver called gravity assist.
It was a critical event for us.
The idea is to fly close enough to Earth to allow its gravity to slingshot Juno towards Jupiter with a lot more energy. The team needs to fire the main engine twice to aim Juno towards Earth. Finally, on October 9th, 2013, Juno hurtles around the Earth, getting a boost in speed of over 8,800 miles an hour.
It worked. We're traveling at about 39 kilometers per second after the Earth flyby, which is fast, obviously.
Juno becomes the fastest artificial object in history. And before it leaves Earth forever, it captures a unique video.
For the first time, a movie was made of the moon and the Earth and the ballet between those two bodies.
I was actually almost brought to tears because it was just so beautiful.
The next phase of the journey is known as Quiet Cruise. For 3 years, the team monitors Juno's progress using the Deep Space Network, 3 huge antennas that take turns tracking as the Earth rotates. They also use this precious time to practice for the biggest moment of the mission, Jupiter Orbit Insertion, or JOI.
We planned everything exactly the way we needed to, and we know exactly what has to happen. And the question is it going to happen that way?
The stakes at orbit insertion couldn't be higher. If they don't get it right, Juno could slingshot around Jupiter and be lost forever.
Now we just have to sit and bite our nails and pray that everything goes just right.
John Bordy, Juno navigation team lead, the man of the hour. You were front and center in that control room. What was that like to be telling people what was happening?
I mean, it was stressful for sure. But at the same time, I was really relieved when we saw the main engine fire. I mean, you could see it clearly in the tracking data, like we thought we would. But yeah, it was intense and stressful for sure.
Now, the Jupiter orbit insertion has happened, but your job is far from over, isn't it?
That's right. I mean, really, things get more busy for us now, because once we get into these 14-day orbits, we're doing a maneuver every 14 days to target the next longitude. So,
well, you've made the first big step. Congratulations on that.
Thanks a lot.
And good luck going forward.
Thank you. It's a relief.
Still ahead, up closer than ever before.
We're actually going to get to image the poles for the very first time.
What picture do you want to take through Juno's lens?
Anybody can actually be a part of history.
You can feel the anticipation building.
It was so tense.
Juno, welcome to Jupiter.
Everybody, man, you're the best team ever.
We hit our burn targets within 1 second. And that's how well the Juno spacecraft performed tonight.
And now the fun begins.
It's time to get a close-up view of that gas giant planet. For decades, scientists have been studying Jupiter mostly from afar, and they're about to get their closest look yet. But what do you want to see? In a space mission first, anyone can help decide what groundbreaking images Juno sends back to Earth.
In North America?
Hey, Jupiter, where are you?
In Australia?
Well, hang on. There it is. I can say Jupiter. Haha.
And around the world, amateur astronomers are answering NASA's call to join the Juno mission.
The amateur astronomers are what's going to make this work.
It's part of an unprecedented decision to let members of the public control Juno's camera, the Juno Cam. For the first time ever, anyone who wants to can visit the mission website and help decide which locations on Jupiter should get a Juno Cam close-up.
To my knowledge, there's no other mission that's ever done anything quite like this before.
It's an amazing opportunity. Because of Juno's unique polar orbit, JunoCam will pass over parts of Jupiter no one has ever seen before.
Every orbit is going to be mapped out, and every orbit we're relying on the public to vote on the images so that we know what they want.
But first, NASA has asked amateur astronomers to make a short list of Jupiter's most amazing storms, swirls, and beauty marks for the public to vote on.
Because the atmosphere is so dynamic, you need up-to-date pictures to say which storms are where and what's developing and what's dissipating.
We hope to see Jupiter at around 8:45, just a little few minutes after sunset.
Christopher Go is part of that army of citizen scientists.
Again, same direction.
Now hard at work imaging Jupiter for the vote in Toronto.
We need to crop the data.
All right, how's that for Jupiter?
Anthony Wesley is doing the same from the outback of Australia.
We're just so lucky to have a planet like Jupiter. It's so large that we can see it easily even through small telescopes.
Anthony and Christopher record black and white images of Jupiter to their computers. Then they add a series of color filters.
With a combination of red, green, and blue, you can just go to any software like Photoshop and convert the monochrome into a color picture.
After the vote, JunoCam will take extreme close-ups of Jupiter, and the raw images will be transmitted back to Earth to be posted to the JunoCam website. NASA's also counting on the public to process those raw images into full-color pictures.
Having first-hand involvement in a spacecraft and having the data available to the public is something very exciting because it's like everybody's going to have the discovery at the same time.
Those discoveries promise to be spectacular. Juno captured this amazing glimpse of Jupiter and its moons during final approach.
This is the king of our solar system and its disciples going around it. It's harmony at every scale. We're finally able to see, with real video, real pictures, this motion, and we've only been able to imagine it up till today.
It's a tantalizing hint of the pictures to come. Coming up,
we know exactly what has to happen.
We'll take you inside the final moments to Juno's arrival.
We're going to go into the throat of hell.
I'm Dan Riskin here at Jet Propulsion Laboratory. Now, already this journey has been record-breaking. Juno arrived at Jupiter as the fastest human-built object in history, and now it's the critical part, Jupiter Orbit Insertion, or JOI. Juno has to slam on the brakes to get into just the right orbit around Jupiter, and if it fails, the whole mission is lost.
It's game on. Juno has arrived at the harshest planetary environment in the solar system.
The first time we're going to see how bad it really is when we have to fire the rocket motor for the orbit insertion. So we're really piling on unknowns on top of unknowns.
Juno is about to be captured by Jupiter's gravity and go into orbit around the gas giant. But first, it must slow down its velocity by about 1,000 miles an hour.
It's a really big deal. That rocket motor has to fire at the right time, in the right direction, for the right amount of time. Everything's riding on it.
It's been 5 years and just under 2 billion miles. That long, emotional journey has led to this high-pressure moment.
If it doesn't go just right, we fly right past Jupiter. We don't come back.
As Juno approaches Jupiter Orbit Insertion, or JOI, it's traveling at 121,000 miles an hour. Way too fast to get into orbit. Glenn Orton is the Juno coordinator of ground-based observations. When he's not directing ground traffic at JPL, he's navigating the high-speed heat of the racetrack.
When I'm on the track, clearly I'm trying to go as fast as I can. Juno is also trying to get to Jupiter as quickly as it can. If you're driving on the freeway pretty fast and you know your exit is coming up pretty soon, you've got to slow down to make it off on that exit, or else you know something catastrophic is going to happen. In the same way, Juno has a huge amount of speed on its way to Jupiter, and when it arrives, it needs to slow down just enough and just at the right time to make it down to its own cornering, that is, into orbit around Jupiter.
With Juno, No one's actually in the cockpit with their foot on the brake pedal. It's been pre-programmed with an exact sequence of events.
The Jupiter orbit insertion is critical to being able to do the mission at Jupiter. Critical maneuver begins when Juno fires its thrusters to spin up, to stabilize itself.
It has to spin 90 degrees so that the main engine is facing forward at just the right angle to get into Jupiter's orbit.
The main engine fires to slow the spacecraft down from the fastest man-made object in the solar system to something that will actually orbit Jupiter.
To pull this off, the engine has to fire for exactly 35 minutes to slow the spacecraft enough to be captured by Jupiter's gravity and go into the correct orbit.
10 minutes is not long enough. It doesn't get us there. 15 minutes is not long enough. It doesn't get us there.
Maybe it fires and we don't go into orbit at all, or we go into a very strange orbit, or the whole spacecraft could blow up.
If JOI doesn't burn at all, we're going to be in a 680-year period orbit. So that's end of mission.
The date of Jupiter orbit insertion has arrived, the 4th of July.
All stations on Juno Core, it's time we see the tone for minimum burn timer. Almost there. All stations on Juno Core, we have the tone for burn cutoff. Welcome to Jupiter.
It's almost like a dream coming true right here.
The relief is only temporary. Now, in orbit around Jupiter, the pressure is on to learn as much about the planet as they can before the deadly radiation destroys the ship.
Jupiter is pretty jacked up with this giant, powerful magnetic field, and it may well kick the living daylights out of the Juno spacecraft.
For the first 2 orbits, engineers will brace the spacecraft for its grueling 16-month run of science orbits.
It's always possible after a big maneuver like the JOI that something will go wrong.
Is it surviving the radiation? Are the instruments all in working order?
To make the measurements of the inside of Jupiter that we wanted to make, we have to get really close to Jupiter. We have to be within 5,000 kilometers of the cloud tops, 2,000 miles. To do that, we have to be deep in the radiation belts of Jupiter.
These will be the most challenging orbits ever attempted. Long, elliptical loops over Jupiter's poles will duck in and out of radiation belts as quickly as possible.
There's a place where you can go really close to Jupiter and miss most of the radiation. And we're taking our shot and running through there.
So Rick Nyback, project manager for the Juno mission. Is Jupiter orbit insertion, is that the scariest moment for you? Or if you look back over the whole journey from planning to launch, where's the scariest part been?
Launch was pretty scary because that wasn't totally under our control. But tonight, the thing that I was most nervous about was the main engine started. It felt like my heart stopped and restarted when the engine started because I knew there was a radiation peak right before the main engine burned. And so once we got through that, I felt, you know what? Everything's working just as we thought, and I was pretty confident we'd complete the main engine burn. But to do it within 1 second, incredible. I mean, how good is our team to do it that tight?
They're pretty good. I'm pretty impressed, and congratulations, and we look forward to the science that's going to come next.
Thank you very much.
Up next.
I think everybody wants to know where we came from.
Closer than ever before to unlock Jupiter's secrets.
I'm in the press briefing room at Jet Propulsion Laboratory, and Juno's navigators have just nailed the most difficult part of this entire mission, and that is to get the spacecraft into the correct polar orbit around Jupiter. Now the pressure's on for the project's scientists to get as much data as they can about this place before the intense radiation coming off of it destroys their spacecraft and their instruments. They have just 20 months to answer some of the biggest scientific questions ever asked.
What we're trying to do with Juno is to try and understand what's inside Jupiter.
Maybe we'll find something and say, how the heck did that happen?
It's a race against time. With 9 ingenious science instruments in just over 30 orbits, Juno will probe deep into Jupiter's atmosphere, down to its inner core, to discover the origins of the planet, seeking the answers to fundamental questions of life on Earth.
We really don't know how life formed. It's a big mystery.
Jupiter is the key, really, to understanding how do solar systems form, where do planets come from, ultimately, where do we come from?
The best shot for learning about the origins of life is water. The microwave radiometer will peer down beneath Jupiter's clouds to measure this most basic component of the planet's makeup.
The reason water is very important to figure out is that it tells us a lot about how and where the planet formed.
Did it form close to the sun or far away from it? Did it form from gases or from chunks of ice? The answers could tell us about how our own planet came to be.
Perhaps the role that Jupiter played in the formation of the solar system, kicking the icy planetesimals about, maybe drove water in to Earth.
To measure Jupiter's water, the MWR will measure microwaves or radio waves coming up through the clouds and use those to calculate the temperature at different depths. Juno's project scientist Steve Levin explains.
The MWR on the spacecraft is a radio receiver. It's like this phone. Your cell phone is a radio receiver. If I stick it in the water, you can see that I'm losing signal on the phone. The radio waves can't get through the water to get to the phone. So when our spacecraft is seeing the radio waves that come from inside Jupiter, we can figure out how much water was in the way in Jupiter's atmosphere.
The MWR will map the entire planet to discover the total water content, which could unravel the mystery of how Earth got its life-sustaining water. Next in Juno's arsenal is the Gravity Science device, basically a radio dish. The signals from this will explore what's happening in the deepest interior of Jupiter and reveal one of its biggest mysteries. Does Jupiter have a core?
We don't know how the mass is distributed inside. Are there separate layers, a core of rock, and then a layer of water, and then a layer of hydrogen? Or is it all mixed up?
They'll be watching how Jupiter's gravity affects the speed of the spacecraft as it orbits around the planet.
Using the radio dish that will be sending signals to the Earth, we look for the Doppler shift that tells us these little wiggles in the trajectory as Juno flies over the planet. And that will tell us about the distribution of mass inside.
The magnetometer will give us details about Jupiter's massive magnetic field. This instrument will tell us more about how planets work. What is the makeup of the interior that drives that magnetic field? A simple experiment shows how the magnetometer works like an everyday compass.
If I sprinkle some iron filings on top, you can see that there's a magnetic field, and the iron filings line up with the direction of the magnetic field lines. As I move the compass around the magnet, it's telling me which direction that magnetic field goes. When our spacecraft is at Jupiter, we have our magnetometer that can measure the direction of the magnetic field outside the planet. That tells us about the dynamo region inside the planet where it's generated.
How are gas giant planets formed? What is the interior made of? The magnetometer will help answer those questions. Just like the magnetic fields of the polar regions here on Earth, Jupiter's magnetic fields also create a breathtaking light show.
Juno will be the first spacecraft that really flies over the poles of Jupiter. And that allows us to look down on the aurora and fly through that region where we think the charged particles are being accelerated.
The ultraviolet spectrograph will examine the auroras by breaking them down into their different colors. The Jade Ion device studies the particles that slam into the atmosphere, creating the powerful phenomenon. As Juno approaches, planetary scientist Jonathan Nichols is watching closely.
It's like Christmas every day. We're getting new data, we're getting new movies like this. The auroras look different every day.
He's worked for a decade capturing Jupiter's auroras from the Hubble Space Telescope. Now, he'll be able to compare them to the up-close data that Juno gets as it flies right through the magnetic fields.
We can see what is going on in Jupiter's magnetic field, and we can correlate that directly with what we're seeing with Hubble, and that will really tie down the processes that are causing these auroras.
Measurements about the interior from both the gravity science dish and the magnetometer will help answer questions about Jupiter's biggest beauty mark, the Great Red Spot.
See the jets on the surface, they're beautiful. But are they surface manifestations? Do they just live on the skin? Or do they extend all the way down to the dynamo region, basically 6,000 to 10,000 kilometers deep?
Through more than a year's worth of orbits, Juno's incredible science tools will beam home some answers to those huge questions.
I think everybody wants to know where we came from and how we got to be the way we are. And Juno will tell us about how Jupiter formed and how Jupiter influenced what was going on in the formation of our solar system. Basically where we came from.
Still ahead, after Juno has done its job, it'll be sent to its fiery death.
If you go into Jupiter, you're not coming out.
Why Juno must self-destruct. Here at Jet Propulsion Laboratory, scientists are now paying close attention to the health of Juno. Because now that it's at Jupiter, it is getting pummeled with radiation. With each orbit, that spacecraft and its instruments weaken, and they cannot afford to lose control of that spacecraft, because if they ever did, that could prevent the biggest discovery in the history of science.
After nearly a year of science, Bolton's team is going to send Juno on a one-way trip down into the storm clouds of Jupiter.
If you go into Jupiter, you're not coming out. The friction's going to start to burn it up and tear apart the spacecraft, and it's going to eventually get crushed.
There is no way Juno will survive, and that is part of the plan.
Juno is the first mission that I've been on where there is going to be a definite end, and we'll have to say goodbye to the spacecraft, and it's going to be very sad.
Sad, but necessary. The reason for Juno's fiery exit is to protect Jupiter's ice-covered moon, Europa. Scientists suspect this place is our best shot at finding alien life in our own solar system. That spectacular prospect means no trace of Juno can remain. Juno was built to be as clean as NASA could make it, but there's still a chance it harbors microbes from Earth. The consequences could be devastating.
Suppose we find life on Europa. You would really hate to do that 50 years from now, dig down through the ice, spend all this effort, and then have to say, but I don't know if it's life from Europa or contamination from Juno 50 years ago.
NASA is not taking any chances. They'd rather destroy Juno than risk any Earth microbes getting to Europa.
The best way to get rid of the spacecraft is to send it into Jupiter, let it burn up and get crushed, and then we know it won't contaminate any of the other moons.
So, once the mission is finished, the team will send Juno into the most hostile planet in the solar system.
We'll fire the thrusters for a fairly long time. We have to slow the spacecraft down enough so that instead of skimming the cloud tops, we're lowering that altitude so that we actually impact Jupiter at closest approach.
As the spacecraft starts to enter into Jupiter, it'll start to feel friction on those solar rays, and the spacecraft will start to come apart. It'll also start heating from that friction, like a meteorite heats when it comes into Earth's atmosphere. So it'll start to burn up.
Jupiter is huge. It's 11 times wider across than the Earth is. And when you send a spacecraft down inside it, eventually the temperatures and the pressures get so high that they will sterilize it.
We have an emotional attachment to these spacecraft, but knowing that they did their job and having a definite end to a mission that discovers incredible things about the solar system is a fine way to go.
It's going to be sad for all of us. At the same time, I fully expect that by then we will have revolutionized our understanding of Jupiter and therefore of solar systems and how planets form. So it'll be bittersweet as well. It'll be not just, I'm sorry that Juno is gone, it'll also be look back at all the wonderful things we've accomplished with that spacecraft.
The team of people behind Juno have already accomplished so much, from that high-speed approach to the data recorded when Juno first entered Jupiter's radiation belt. And even though orbit insertion is complete, the mission is really only just beginning. It's going to be an historic 20 months of science, and we can't wait to see the discoveries that this team has in store for us. I'm Dan Riskin. Thanks for watching.
Welcome to Jupiter.
It's been the hardest thing NASA's ever done.
It's almost like a dream coming true right here.
There's a saying, it's not rocket science. Well, today, yeah, it really was rocket science.
It's just incredible. The team is on cloud nine. We're all on cloud nine.
What a milestone in American history.
Juno sang to us, and it was a song of perfection.
We did it. We conquered Jupiter.